Você se chama de novo. Não sabe se ele recebeu o convite ou não recebeu. Acho que agora tá. O microfone tá funcionando.
Vai ver, ótimo.
Okay, hear you now.
Okay. Can I hear me? Can you hear me?
Yes.
Can you hear me now?
Yes, I can hear you.
Great. Excellent. Thanks. Oops.
It's fine. I just turn it on and off because I think I'm going to switch to a presentation anyway. So.
Oh, great. Okay. Thanks. I'm just going to plug in the... Okay. Can you hear me now?
Yes.
Yeah?
Yeah.
Oh, brilliant. So while you are talking, I'm going to turn the computer towards the audience so that you can hear, you can see them, yeah?
Okay.
That'd be fine?
Yeah.
And I was just commenting that I read the article on New York Times about you were at the computer for, was it Games for Change, wasn't it?
Yeah, yeah.
Was it last week or 2 weeks? 2 weeks?
Yeah, it was last week.
Was it last?
Yeah.
Oh, great. Okay, this is a very informal meeting, so it's up to you, the format and the content. It's a great pleasure and an honor to have you online. So let me introduce you to the audience.
Okay.
So here is Zoran Popovic. Please go ahead and let's get back to talk to you. In case there is any question or anything, we can sort of try a Q&A. But you see, I don't know if this works, but it's great. You can talk to, I don't know, 20 or 30 minutes, up to you. Yeah?
Okay, good.
Go ahead, go ahead.
All right, so I will switch to the projection of a presentation, and I'm assuming this is projected on the screen or something.
No, it's not. It's not being projected. No, I'll try and make that. Yeah, make sure we have that.
All right, so is this visible?
Sorry.
Let me just. Okay, can you see the screen?
Yeah, well, we're projecting it now. Just 1 second. We're turning a.
Okay, so I can just start talking. So as an introduction, I am a director of Center for Game Science at the University of Washington, where we do a lot of research about how to apply different methods of computer science and game-based learning towards trying to achieve sort of maximal outcomes in any classroom. But I also founded a nonprofit called Engage Learning that's actually deploying a lot of these technologies we developed to actually apply directly to not just other games, but to the whole curricula. So, for example, we're talking to entities like McGraw-Hill and Scholastic to take their curricula and turn them into this engaging and infinitely adaptive version of itself. All right, so our fundamental goal is to figure out how can we get any classroom with any kind of teacher and any kinds of students to get to up to 95% of the kids reaching mastery in a particular concept. Now, of course, that's a crazy lofty goals, but just to show you that some of those things actually are possible, we ran an algebra challenge over 5 days in Washington State, and later on in country of Norway, and later on in Minnesota, where we basically asked all teachers to try for an hour and a half to sort of have this activity with kids, which is about solving complex linear equations. And here, and we were using an adaptive version that specializes for every unique kid of a game Dragon Box, which by itself is not adaptive. And here are the outcomes we were able to achieve. So as you can see, this is the breakdown for every grade on how many kids reached mastery of it being able to solve a complex linear equation. So this, I mean, on average, this is 93% over the entire K-12 spectrum. So this is pretty crazy numbers in some sense. So let me just give you a sense of what we think is key to being able to achieve something like this, with or without games in some sense. What we're doing is basically trying to figure out how to optimize the entire process. So instead of just optimizing for a curriculum or just optimizing a student or the interactions with a student, we try to optimize all of those aspects together in such a way that we have the best possible outcomes. And that's kind of the set of things we've been focusing on. The key things that we think are required here is what I call infinite curriculum, which of course is not necessarily infinite, but it means that it has almost 10 to 100 times more content than the standard curriculum, and that's really required if you want to have sufficient amount of variability for all students. Then we have a way of using data to optimize the pathways towards discovery, and we optimize for both mastery and engagement at the same time, and we deliver this whole thing in a platform that will briefly tell you something about. So let me just give you a quick sense of what it means to create a curriculum that can vary itself in all possible ways. Let's take a simple example of sort of the standard way things are adaptive today, which is you have a certain module, you have an assessment, and if you don't do so well in the assessment, well, you go back to the module and do the same thing. It's kind of, you know, our education is like that, but really, in any way in which games are adapting, they're adapting in the very same way. So we just kind of continue this. The problem with this is that there's no reason to believe that going back to the same module and doing the same things over and over again would necessarily produce learning, and it certainly wouldn't present learning in the most effective way that would sort of be just right for every student. So instead, we're looking at finer grain specialization, which means that, let's say we have a problem like this. This is a math setup, but it's very similar for games, as I'll show you. So this, you know, here you're trying to figure out which number is larger, and if you start thinking about what is the process that the kid needs to think about, it sort of goes like this. Based on different conditions on different digits, the student is supposed to go through this process. And so we have basically a language, what we call a thought process language, where we're able to encode this thing. And the nice thing about it is that that allows us to now look at, for any problem that we're able to pose, it's going to be going through a particular path of this thought process. So for example, if I wanted to look at compare 313 by 324, that particular problem exercises this particular thought process. So its path is DDS, if you will. So what's interesting is that when we represent things in this way, we can do many things. We can automatically generate problems that go through any one of those paths. We can analyze progressions that already exist and synthesize arbitrary number of new problems. So let me give you a sense of what this means. If I look at, for example, how one curriculum is trying to present a sequence of problems, in this case it's a jump math curriculum, it has this pathway. If I look at Singapore math, you can see that there's very little overlap actually between the two processes, that they take very different progressions on this same relatively basic problem that they're trying to solve. But the most important thing is that neither of them is optimal or comprehensive. And so, for example, what we can do is now take any kind of game and then represent it in the same way, such that we can figure out exactly the space of all possible problems and exactly how they're difficult. So here's another thing that we can do. In this case, here I'm showing a video. Hopefully this is showing up on your screen, but these are automatic explanations generated from tracing through the thought process language. In this case, solving a complex puzzle problem that requires both reasoning about fractions and spatial reasoning. And what's nice about this is that for any level that we create, we automatically generate explanations. That in this case, it's an explanation from beginning to an end, but you can imagine how this can be used any place where a student is stuck. We can get just the right, just-in-time explanation of exactly what they should be thinking about to do next. And so this one representation ends up being very powerful in terms of allowing us to do many things at the same time. Most importantly, perhaps, is that when things get really complex, we have a way of reasoning about this. So in this case, imagine a problem like this where you have to put the right parentheses around these problems. if you look at the space of all possible problems that can be generated here in terms of their difference in their difficulty, you get space this large. If I zoom in to one of these places, you can see that every little circle has a bucket of maybe hundreds of problems that are exactly equivalent according to their difficulty level. So we automatically generating this big map of space simply by describing what the students should be thinking about. And that ends up being very powerful in terms of our adaptive processes. Interestingly, we're able to do the same thing for generating text problems. So in this case, actually it would be interesting to see how much this could actually work in Portuguese or Spanish. But really what's interesting here is that the student can pick any of the context. So student can pick Harry Potter, science fiction, medieval literature, or I don't know, World Cup soccer even. And basically try to get all the mathematical content exactly in that domain. So let me show you some examples of this. Let's say we have a medieval context and we want an expression, we want a set of problems that exercise exactly this kind of computation for students. This is the kind of stuff that we're able to automatically generate. So you can basically see a fairly complex sort of narrative around some of these problems. I'm going to switch to some more ones. So this ends up being is sort of ability for a student to learn the entire algebra in terms of word problems exactly in the world that they like. Not only that, but they can actually create these characters like Cecilia, etc., and then create other characters and define who's friends with whom, and that would drive the actual narrative. Here's another example, in this case slightly different expression, but now in Harry Potter domain. And what you can see now, we have dizziness potions and long forgotten charms. Here's another set of examples. The top one here is the Quidditch, which is that game that they are playing.